So, hello everyone, and welcome to episode 12 of Echoes from the Field, the Stride podcast exploring the people, technologies, and the ideas shaping land seismic. Today, I'm delighted to be joined by Sandeep Kumar Chandola, a highly experienced geophysics leader at PETRONAS. Sandeep began his career as a field geophysicist with ONGC in India and has since spent the intervening years designing and optimizing seismic programs and also evaluating new technologies. And today we're going to discuss how land seismic is evolving, the value of high density acquisition, the challenges of scaling to much larger channel counts, and what the next generation of land seismic systems must deliver. So Sandeep, welcome to Echoes from the Field. Delighted to have you.
Thank you, Mike, and good to be talking about seismic for a change. Usually we talk about cricket more. So good to be on this.
I might sneak in a cricket question later, but not everyone will know what we're talking about, unfortunately. Looking back across your journey in land seismic, what do you think changed most fundamentally over time? And also, which long-standing challenge has the industry yet to solve?
Yeah, if I look back at my career, which spans about 4 decades, and when I started as a very young geophysicist, obviously one of the things which has changed dramatically or significantly is the channel count and the sampling. I still remember my first 3D survey in India was shot using 2 DFS5 units because one DFS5 units had 120 channels. So we cascaded 2 units, analog systems with 240 channels. Imagine 4 receiver lines like a streamer survey. And from there, we have come a long way, with the improvement in the technology, the 24-bit recording systems, and then large channel counts, miniaturing of the equipment, a movement from the geophone strings, multiple geophone strings to single nodal systems. I think that has been a revolution, and that is something which probably has been a remarkable improvement, both onshore and in the marine environment, if you see, which has helped us in acquiring high definition data sets which can last through the life of field, which is probably the most remarkable change I would say I've noticed during these 4 decades of my career as a geophysicist.
And what about challenges which industry hasn't yet solved? Is there anything which stands out to you?
Yeah, so one of the things you see, we in geophysics, we are also limited by the earth, which is probably the biggest filter we work with. And if you don't record it, you can't recover it. There is no such technology as of today which can recover something which has not been recorded. So one of the challenges I still see is resolution, because vertical resolution is limited by the frequencies which you can send through your target horizons, geological horizon, and also the attenuation the earth delivers. So to me, resolving those thinner beds or ultra thin beds, obviously it's still a major challenge. We have done very well when it comes to imaging beneath complex overburden, for example, subsalt imaging, precarbonate imaging, sub-basalt imaging. We have done pretty well in that domain, and using ultra long offsets to see deeper, we have done pretty well. But in my view, one of the biggest challenge remains in addressing the issue of resolution and also to carry the advantage of imaging through the geological modeling. There is still a bit of a disconnect when we talk about, the modeling, the geological modeling, the reservoir modeling. Sometimes it is not being updated at the same scale or at the same pace as the new data coming in. So that is an issue of technology, probably a pace, turnaround time, which still, I would say it's a work in progress.
Yeah. Okay, thank you. So moving on, where do you see the biggest gap today between what subsurface teams need from seismic, so the greater definition, increased certainty, faster decision-making, say, and what acquisition crews can practically deliver in the field with the tools available to them?
Yeah, it's a very good question. And you see, for me, someone who has been practicing geophysics for a long time and also got the opportunity to lead the geophysics team in PETRONAS for several years. Sometimes what happens, the geophysicist, when we deliver a high quality, high definition seismic image, we think the job is done. But actually the job starts there for an interpreter, and they need to take it through, as I said, interpretation and ultimately how it is improving their subsurface model. then QI comes into play, like, as a bridge between geophysics and geology, seismic inversion. And then, of course, you have to look at the geological modeling and static models. So that is where probably I would say the solution which we deliver as geophysicists should be fit for purpose, right? If it's an imaging issue, I would say it's relatively simple. I don't want to oversimplify or, demean the effort, but delivering a good seismic image is probably the first step. The more difficult challenge the asset teams face in terms of subsurface is resolving complex reservoirs, like pinning down the reserves, the numbers, because that impacts the economics. And most important is the turnaround time. We still take months to deliver a data set. So that sometimes a great data set a little too late is of very little value. A good data set delivered on time has a much higher value. So the pace is equally critical in my view.
Yeah, I was thinking as you were talking, because we've introduced Stride Lens, where you get an image, and it's not the ultimate image that you could get from a big processing house after several months, but it's a very good image, say within a week. I was wondering how quickly you could get the interpretation side to run, as in, could you in the field get real-time feedback on that or not? I'm suspecting not, otherwise people would be doing it. But yeah, I was just thinking through my head, if I can get you an image, a processed volume in a week, could your interpreters turn around their bit to go, actually, we need X, Y, Z, while you're still in the field acquiring?
Yeah. And this is not something new. We have been discussing this for decades now, in 90s as well, when the technology of lossless compression, data compression and transmission came into play. So one of the things we were trying to do is to transmit the data, the field data, in near real time to the processing center.
Yeah.
Right. And because the capacity in the field was limited and the bandwidth was the limitation. But we did, the attempts were made. As of today, you see the compute capacity has grown significantly. And in field also, we have systems bigger than the processing systems in the 90s, right? So that part, it is something which probably I would say, if not the final data, but for example, the pre-processing, it takes a lot of time. And sometimes the field geophysicists have a much better understanding of what is going on in acquisition. So I think it's a good probably approach to try to pre-process the data in the field and transmit the conditioned data rather than the raw field data to the processing center. That itself could be a big help in reducing the turnaround time. Yep.
Yeah, that's certainly doable today. So that's good to hear. Okay, moving on. So at Stride, we're definitely seeing a clear shift towards high density acquisition across increasingly large surveys as well. So survey sizes are going up, as are the number of channels and shots, and that's resulting in much higher channel counts on each survey. From a geophysical perspective, what value does denser spatial sampling unlock? And are there particular environments or applications where it can deliver a real step change in subsurface understanding, in your view?
And actually, I think sampling is probably, is one of the most critical aspects of our survey design and data acquisition. And what has improved in the last decade or even more is that with these large systems, large channel counts, we have been able to sample the subsurface much better. And it's not only when we talk about the sampling of the wave field, we are not talking about the signal only. It's also the noise, the coherent noise, the diffractions. So one of the things we always compromise in sampling, we used to, is the sampling of the noise and, the coherent noise, because signal usually could be reasonably well sampled in the past as well. So that has improved a lot. We have tested multiple technologies because, we in PETRONAS, we are primarily an offshore and OBN company, but we also have some onshore projects. My past life in ONGC, it was predominantly my job was onshore. So what we have seen is when we are able to sample the wave field optimally, you can, in processing, you can choose, what do you need from that data. So that's probably critical. But if we have not recorded it, as I said earlier, if we have not sampled it, it's very difficult to reconstruct the data beyond a certain limit, because although we have very advanced reconstruction algorithms, still what it doesn't reconstruct is the noise. It's about signal, and it's also about the signal to noise ratio. So I think that is something which high density acquisition delivers, and that data set is useful as I said, through the life of field. It can be used for exploration with a certain sampling. It can be used for appraisal and development. And then we can repeat this data. When a question of 4D comes, we don't have to repeat the data with the same sampling, because the idea is not to produce a fantastic static image. The idea is to monitor changes. So that is very important. And then again, when we talk about the monitoring, say for CCS purpose, the business drivers are different. I think we need to look at smarter ways of monitoring, because we are not into a PSC domain. So the budgets are limited. So how could we design a survey smartly, probably of a lesser aerial extent, but making sure that the key potential leakage points are captured well. Same goes to geothermal. Our targets are likely to be shallower, so you require much denser sampling, but probably you don't require such ultra long offsets like we require. So those are the things where we could make it fit for purpose, and we as geophysicists have a key role to play in how we make it work in a cost-effective manner.
Thank you very much. Can you share an example of where increasing the density has really delivered a meaningful improvement in the subsurface image, or altered the decisions that followed?
Yeah, there are quite a few examples that, where we actually have managed to achieve that. One of the earlier surveys we did here was an OBC survey. When we started the survey, it was, and OBC surveys are very similar to the land surveys in many ways. So there we started with an exploration survey, and when we were mobilizing, there was a requirement from the development team that there's a producing field inside where they want to have a seismic coverage, but the exploration design doesn't actually fit. It won't meet the requirements of development, although it meets the requirement of exploration. So we had to go to the drawing board again, and we kind of quickly customized our design, doubling or tripling the trace density. And then we got some at a relatively lower cost. Because the crew was there, we just had to infill with some, closer receiver sampling, but a much denser shot sampling, which is cheaper in the offshore environment. So in the end, we produced a unified data set, which was fit for purpose for both exploration and development. It is still being used by the team a decade later. And then more recently, in an onshore environment, MPM, currently we are acquiring data in a frontier area for MPM. So actually, when they came to us, it was a 2D program. So I actually kind of challenged the team. I said, okay, what if we delivered to you a 3D program at an incremental cost increase, not a substantial cost increase? So they got interested. So I asked the team to keep the number of shots the same for 2D as for 2D, because it's a dynamite survey. It's expensive. I said, plaster it with very dense receivers in line, keep a relatively sparser cross-line sampling, the line spacing. And we came out with a design which is about 20-25% higher in cost as compared to a 2D. So today now we are acquiring that data set. And we believe if there is prospectivity, will be good enough to drill a well. But the 2D in this case was unlikely to be enough, because the subsurface is complex and the line spacing was too sparse. So we believe that this data set, we call it an exploration grade 3D, should be good enough. And we are also combining that with compressive sensing to further be able to reconstruct the wave field in an even more tighter manner. So this is one example. We are yet to see the results because, it's early stages of acquisition, but I believe that this could be a very, very, I would say, interesting experiment, which we hope to replicate because we have more onshore work coming in the next 2 to 3 years. And if this works, then we would try to persuade our asset teams to convert some of the remaining 2D campaigns into exploration grade 3D.
Yes, glad to hear that discussion's happening at your end as well, because it's something we ask clients a lot. People will say, I want a 2D, and then we kind of point out to them for relatively little, they can go up to maybe a sparser 3D, but it's a 3D and the value will be huge. A really good example. So thank you for sharing that. So land seismic surveys, as we said, are going up in channel count. When a survey scales from, say, a few thousand channels to maybe even 100,000 or hundreds of thousands. Where do you think the operational constraints begin to emerge? And do you have to make compromises as you go up that scaling journey?
Yeah, actually, you see, it's also largely dependent on the operating environment. For example, Middle East, when we have large expanses of deserts, it's relatively easier. What we talk about when we talk about the cultural noise there is quite different from what we talk about, say, in Malaysia or India, right? So that to me is one of the key constraints, because when I have worked in India, I worked in Middle East, I worked in Malaysia. So the challenges are quite different. If you have a lot of cultural noise with people, vehicles moving around, obviously controlling a large spread becomes challenging. And especially in a nodal environment, till recently, when there was no way of doing a real time QC of the nodes, which is still largely the case. A node health check is one thing, but in
Yeah.
real time monitoring the noise on a cable system versus a nodal system is quite different. So that is challenging. Middle East, you have wind noise, those kind of things, but it's pretty predictable. So you can manage much larger channel counts, and that's the reason the largest channel counts in the world are in the Middle East. In Malaysia, it is the terrain, the swamps, the undulations, the plantations. So I believe that is probably where the portable equipment becomes quite handy. That's
Hmm.
also an opportunity. So when carrying 12 geophone strings or 24 geophone strings, it's practically impossible. So when you go to a single node, a light node, which you can plant, put a hammer, and then, move on, that becomes a lot more easier. And you can play around with your sampling, means the spacing and all. So I think that is a challenge when we talk about the operating environments. That's the biggest challenge. And the miniaturing of the systems like nodal system, it's probably a solution, a good
Hmm.
solution to that challenge.
That's obviously good to hear. Thank you. So I guess contracts are also increasingly proposing nodal systems. So I think both operators and acquisition contracts have seen the benefit. They're proposing nodal systems for larger and denser surveys. From an operator perspective, what should you consider or examine to determine, is a system actually scalable to the level you need rather than just able to support a large number of channels? So how do you work out if you need to go denser and bigger? What do you look at?
Yeah. Actually, of course, one of the things is when you look at the sensor itself, and I believe majority of the nodal systems are almost in that sense are roughly comparable. If you
Yeah.
have a based system, for example, versus a geophone based system, I think onshore very few systems would be nowadays, you know, uh, geophone based systems, or there may still be some systems, but when you go to OBN, largely most of the systems are still velocity sensors. And there is a
Hmm.
reason, the power requirement and all. So they are still 14 hertz geophones and all, whereas like the new systems, onshore systems, you get a lot of MEMS based system. So that is one way. At the low frequency response is critical for us. I'm talking about the sensor side, because the FWI, as you know, it requires low frequencies. And once the noise threshold kind of exceeds or is about the same level as the signal, no way you can recover those low frequencies. So the low
Yeah.
frequency response is one thing. The other thing is operational, which is portability. Again, the weight of the equipment is quite important, and we know that like Stride is an ultralight system, so that is always a benefit. The other thing is also, in our case in Malaysia, for example, the ability to deploy this system in wet areas. I'm not saying water covered areas, but wet areas like swamps, because it's very hard to find totally dry areas like Middle East. So that
Yeah.
also is a consideration, so that you have a spread, a seamless spread. You don't have to deploy hydrophones in between few channels and mix the land nodes. So I think those are few considerations in terms of when we design or when we evaluate nodal systems. Yeah.
Good to hear. Thank you. As land surveys continue to scale to kind of mega crew channel counts, you touched on it earlier, but looking across that receiver spread becomes increasingly challenging. You've got more stations to monitor. In your experience, how much real-time in-field visibility is actually needed to manage data quality, operational risk, crew efficiency? And so if you could pick, what's the minimum you would need to monitor a large crew?
Actually, if you see, When we use nodes, we use a lot of them in offshore environment. And,
Hmm.
the risk is much higher there because the
Yeah.
cost of doing an OBN survey is a lot higher than, in terms of spread, I'm talking about deploying a spread, is a lot higher than an onshore survey. So I would say in an onshore nodal system, the risk is much lower. But we have been using the nodes, offshore nodes for years now. And the failure rate is typically below 2%, sometimes even below 1%. So I would say the risk is very low, right? And all we have in offshore environment is a pre-deployment check. And we do deploy
Yeah.
some QC nodes and we recover them, right? Onshore, as long as, and I was in the field recently looking at, a nodal system, which is from a competitor of yours, but they're very similar. On your iPhone or on your Samsung, you will get that app and you can see the basic health check, right? You can see
Yeah.
the node is red or green or yellow. So what needs to be done? And then seismic data, obviously at the moment, there are some systems which, they're still trying to have some sort of seismic data check. But I would say in an onshore environment, it's not critical as long as you have a robust node which is factory tested, field tested with a low failure rate, and you have the health check which is easy for the workers to understand. You don't need a super technical person to check that. I think the risk is quite low. So I think these
Hmm.
are the health check, in my view, is more on the integrity of the nodes. The seismic
Hmm.
data, I know there will be technology will be there, sooner or later. We will have, it's a question of having the bandwidth or the ability to transmit the data and, to be able to see it, if not for all channels, selectively, randomly, if you pick up 10% or 5% or 2% of the channels, I think that'll be great if we can do that. But to me, in the current state of technology, I think the risk is relatively low. I have not seen cases where we had a significant loss of data. What we have seen is a loss of node. So if
Yeah.
the node is washed away in offshore environment or taken away in the onshore environment, you will lose data. So that to me is a bigger risk than losing the data because of the node itself. Yeah.
It's good, actually. I'm looking forward to talking to your image soon because a lot of the things you've identified as important are what we've introduced in the Halo regs. We've got very, very low noise at the low frequencies. We actually have the ability to stream data, although you need certain coverage in the area, but also wet terrain. So I'm looking forward to having a deeper discussion in person on how close we are to what you need. Okay, moving on. Advanced imaging methods such as FWI are really raising the bar for the quality and completeness of the data that needs to be acquired in the field. You touched on this already, but what information must be captured properly during acquisition rather than reconstructed or compensated for later during processing?
Yeah, as I mentioned briefly, there are two things which FWI relies on. Basically, one is the offsets, and the other one is the low frequency content preservation or enhancement of the low frequencies. So, if you talk about, say, let's talk about the source, because there are two components of seismic recording. One is the source, other is the receiver. So on the source side, if we are talking about the vibrosize component, vibrosize source, then the low frequency side of the source, a lot of work has been done, whether we talk about the maximum displacement sweep or, a low dwell sweep or a, non-linear sweep. So basically, a lot of work has been done and the vibrosize design has been modified. So couple of hertz, we are down to couple of hertz, we get a decent signal. Dynamite by nature is a broadband source, so you record everything from 0 to infinity. So that is a given. Now, and in offshore environment, we are also playing around with these sources. As we talk, we have completed the first survey in the world which has been done solely using a tuned pulse source, no air guns, and is the first hybrid survey. So Shell has done a TPS only survey, OBN survey. What we have done is a streamer survey with nodes deployed. And we are talking about a 12,000 square kilometer of area. So that's a massive survey and we are very keenly waiting for the results. It's very early days now, but you can imagine the amount of investment which has gone into adding TPS and adding the nodes into a streamer survey. So that is the offshore side. But onshore is no different because the long offsets are relatively easier to achieve because you can have these thousands of nodes and you can record 30, 40, 50 kilometers of offset. The other thing is the low frequency side. As I said, the source side, dynamite or air gun or tuned pulse source in the offshore side, and vibroseis as well. So these are probably the critical things. And we have the algorithms nowadays. Now we have moved from acoustic to elastic domain in full waveform inversion, which has given some fantastic results, in our case, especially when you are dealing with the salt or carbonates. The imaging is quite different when we move to the elastic domain. So probably these are some of the key things. And of course, in a good field acquisition, the effort should always be to keep the noise floor as low as possible, and the cultural noise. So if we have these fundamental things working, I think that's critical for the full waveform inversion.
Okay, thank you. So my last question, you spent a lot of time analysing geophysical technology across your career. Looking into the future, what do you think will define a world-class land seismic ecosystem or technology, which can work across multiple industries, so across oil and gas, CCS, geothermal, other subsurface applications? What do you think the future holds on the receiver side? And also, what capabilities of a system are non-negotiable from your perspective moving forward?
Yeah, like we have been talking about, the multiple applications of the same data set. So one of the things I think, and you also mentioned about the scalability of a system, I think it's critical. So nowadays, we know in E&P companies, we are energy companies. We are no longer just hydrocarbon exploring and producing companies. So when we drill a well, nowadays, in a lighter vein, we say we never drill an unsuccessful well. It will either be a hydrocarbon producing bearing well, or it'll be a storage well, right? To store the CO2. We just have to find the right location. So what I'm saying, the objective is not only to pick up those potential hydrocarbon bearing reservoirs, but also those saline water aquifers, right? When we design a survey, which could be shallower or deeper, depending on the geological setting, then we also need a top seal to trap that CO2, which, then we also need to map our containments. Are there any potential fault-based leakages and all? So what I'm saying, that data set is going to serve multiple purposes. So that is why it's quite important to see that once we go in the field, we acquire a data set which is scalable. And if that evaluation should be undertaken upfront, this is my immediate goal for the next 3 years. But in the 5 to 10 years domain, this is how this data could be used. So that helps in designing the survey, and that could be done probably, as I said, at an incremental cost if we are smart enough in having these portable systems, for example, especially onshore systems. Because the receiver side, if you increase the density by, say, 10 times, it's not going to increase your cost anywhere close to 10 times. It would be still a percentage increase, right? Because that's the beauty of the scalable systems. And your source sampling then onshore can be determined. With vibroseis systems, you can still go dense, relatively dense. With dynamite systems, you can stay sparse, right? So that is our major constraint when we talk about offshore. Ocean bottom nodes, we still do not have the technology to scale them to such large numbers, or, to go very dense. Ideally, we would like to go, but it comes at a price. So in my view, that is probably, design is still a critical component. And then scalable systems. And of course, what I foresee is the AI/ML, the artificial intelligence and machine learning based algorithms are going to play a critical role in the future aspects, because one of the things we are looking at is the crew efficiency. Because you would have seen that crew spends, when you do a time activity analysis, a certain amount of time is in deploying the system, right? Troubleshooting the system, recording, picking it up, downloading the data, right? So if we do a time activity analysis, AI/ML can help us in seeing where are those bottlenecks. So ultimately it's time, the crew time, the equipment, yes, but then ultimately it's the crew days or crew hours which contribute to the cost. So to me, if we can use the technology in a smarter way, we could reduce the turnaround time, increase the crew efficiency, reduce the cost. I think so. Those are few things we would hope to see in the systems of the future. And I hope it's not too far. I can still see in my lifetime, hopefully.
I'm certain you will. And going back to your first part of your answer, it's interesting. It's a trend I'm seeing through these discussions, but also business in-person discussions. That concept of one data set serving multiple resources or multiple industries ultimately is certainly growing in people's minds. So yeah, it's a direction of travel which I think we're only just starting to explore, but I think has a lot of potential. Fantastic. Before I close out, was there any other topics you wanted to cover which we haven't talked about already?
Well, I think, yeah, it's also sometimes it's the, educating our users, because
Yeah.
I think you mentioned during the conversation, because our end users are the seismic interpreters or the geologists. So it's very important to have those interactions. And that's why when we have these workshops, or I would say engagements, we should not confine those sessions to a bunch of geophysicists or engineers, because we know what we are talking, but basically it should also involve our end users, the interpreters, the geologists. So I think with more multidisciplinary, more integrated teams, this understanding will improve and strengthen. And that's when the interpreters will also have a better appreciation of the technology, and we will have a better appreciation of what the end user requires, so that we don't over design some of the surveys, and we also are mindful of what is the requirement in terms of subsurface considerations from the interpreter's viewpoint.
No, that makes a lot of sense. Thank you. Thank you very much for joining us and sharing your perspective. It's been a really insightful conversation. So thank you. I think we've highlighted a lot that high density seismic being successful, that depends on a lot more than just increasing receiver numbers. And we've covered a lot of what's needed to operate efficiently at scale. We've discussed that the imaging techniques are becoming more advanced, and the industry must therefore make sure the right information is captured in the field rather than trying to compensate for it later on. We've covered a lot of ground and it's been very enjoyable. So thank you, Sandeep, and thank you everyone listening to episode 12 of Echoes from the Field.